Hello everyone. In this session, I'm going to talk about different ways of managing and understanding the data. We all need to understand that whatever is the kind of machine learning algorithm that we are going to implement based on our data, we need to set the data right. And setting the data right can occur only when you understand the data better. So once you look at the data, have a good feel of the data so that appropriate technique can be chosen. And if there are some kind of manipulation, some kind of modification, some kind of improvisation that need to be done to the data, we need to do all those things before we initiate any kind of a machine learning process. So from that perspective, this topic becomes utmost important. How do I really understand the data? What are the different steps? When someone has given a data to me, what are the different steps that are involved in terms of understanding the data? What are the different kinds of manipulations and modifications I have to do to the data so that it can be used for a good machine learning purpose, so that the machine learns from the data much more appropriately. So here we will be talking about why do we really need to understand the data and manage the data, what are the various aspects of it, and just giving you a very brief overview of the various data structures in R. This is not a session meant for understanding the different data structures. Here it is already assumed that you have a good amount of understanding regarding the various data structures of R. In case you don't have a good understanding of them, you can please refer to my other set of videos covering data analytics using R, where each of the data structure of R has been explained in depth, where you would get a good hold on the various aspects and structures of R, which is more of an introductory part of R. So here I'm just giving you a very quick overview of those various data structures, because we are supposed to work with those various data structures, get modifications done, get improvisations done, with which we would be able to manage the data more and more effectively. So we'll take one data set and we'll try to do different kinds of management aspects with respect to that particular data set. We'll do an in-depth exploration and understanding of the data, taking an example. So this process would be the same. If someone has given us the data and they are asking us to implement an appropriate machine learning algorithm to it, the step one of it is, how do I understand the data? What do I mean by understanding of the data? How do I explore the data in depth? So, a few important points for us to understand here. Any learning algorithm that I am creating, right? Where it could be a classification kind of machine learning algorithm. Within classification, I said there are so many such kind of techniques. Or it could be a numerical prediction where I can use regression kind of techniques, or it could be a complete unsupervised kind of algorithms where we are talking of pattern discoveries or clusterings, any of them, right? All these come under the various machine learning algorithms. Whatever is the machine learning algorithm that I am thinking of, it would be good, it would be effective only if the input data is effective. So if the input data that I am giving to the algorithm is a clean and a good data, probably I can create a good learning out of it. It's as good as saying, if the material for the training is good, the learning will always be good. But if the material itself is faulty material, probably you can't expect a good learning out of that training program. The same logic applies here. So many cases in the real world, we see that the data we come across is very complex with so many interrelationships between the various variables. It's not that straightforward kind of a data, and it has multiple sources. Some part of the data could be in a CSV file, some of them could be in different databases, some of them could be in a text file. I don't know. There are different formats for different kinds of data. So, if you ask me, in the whole machine learning process, where do you spend maximum amount of time? I say it is in this stage where I'm trying to look at the data preparation part. How do I bring the data into a format that R understands, and how do I explore the data? Explore means look at in depth every variable individually. You start exploring each and every variable. Try to find the relationships between the pairs of variables so that you understand the data in depth, the various characteristics of the data in depth. So if you talk about the overall exploration process, we need to have a good understanding of the various data structures that R is using to store the data. What are the various formulas, functions that I can use to get the data from, let's say, a spreadsheet into R and from R to a spreadsheet. So I need to have a good understanding of these various functions. And once I am supplied a data, what are the very common mechanisms that I am going to use to, one, tabulate the data, understand it, summarize the data, get some insights out of the data, and along with that, what are the various visualization mechanisms that are there with the data that is given to me. So these are the various things we are going to look at. We'll take one example, a very simple example, so that we can understand all these aspects more comfortably. First thing, I don't want to spend too much of a time, but the expectation is you have to be very comfortable with these various data structures in R. Majority of the data structures, right, I would be talking about the vectors, I would be talking about factors, I will talk about lists, all in this half a slide kind of mechanisms. We'll talk about data frames, we'll talk about matrix, and we'll talk about arrays. So these are the very common data structures that we are going to use in different aspects of our learning program. The main intention of any data structure is I will be able to manipulate the data more and more comfortably. The moment I know this is the data structure, I would be able to manipulate the data more and more comfortably. I can perform different kinds of analysis on the data because different functions that we come across at a later point, they require the data in different forms. So there could be a few functions which require the data to be in the form of data frames. There are a few functions which require the data to be in the form of a matrix. So we need to understand what each of these data structures are so that we would be able to comfortably convert our data into an appropriate format for the machine to for the machine learning algorithms to execute them more comfortably. So these are the common data structures that I'm going to look at: vectors, factors, lists, arrays, data frames, matrices, etc. So just a quick overview of the stuff. I'm not going to do any of these things in R. I'm expecting you to have a good understanding. So just trying to differentiate between these features. So any ordered set of values of the same type. So they could be of all numeric values, or I can talk about all logical values, or all date values, right? Or I can talk about all characters. So these are a set of elements of the same type that we can call it as a vector. So the types could be integer, numeric, character, logical, everything could be null or NA. NA is the typical word we use for missing values in R, right? Then generally in case of vectors, if I have to combine multiple values, if I have to combine multiple values to a particular variable, I can use a concatenate function or a combine function C. So if I am giving A as C of 2, 4, 8, 5, 12. So A will take values 2, 4, 8, 5, 12. So it would be displaying those values. So this is how we are using the concatenate individual elements so that they can be grouped together. So this is what we are calling as assigning a vector to a variable. So this is a vector of 5 values. The size of this vector is 5. I am assigning this vector to this variable called A. And I can access the vectors and subset of vectors. If I am saying A with a square bracket of 1, means out of this vector pull out only the first element of the vector, which will give me an output of 2, because this is the first element of the vector. Or I can say A 2, 2 colon 4, which is like 2 to 4. So I'll get the output as 4, 8, 5. Or if I'm saying A of minus 3, it means out of this A pull all the things except the third element. Minus is like a negative subscript, right? So it will bring out 2, 4, 5 and 12. So or probably I can say A of C of 1, 3, 5. So I'm saying pull the first element, third element and the fifth element. So which will give me 2, 8, 12 as the output. So this is that basic operation with respect to the vectors that you need to be comfortable with. You can refer to any of the basic introductory books on R, or you can refer to my videos on data analytics using R, the separate code, so that you can understand all these ways of manipulating the vectors and getting the subsets of the subset of the vectors as well. Then the other important data structure that you need to be comfortable with is factors, especially when you are loading the data from a spreadsheet. Your data is there in a spreadsheet, you are getting it into R, and let's say one of the columns in that spreadsheet is a categorical variable or it's a character variable, let's say gender, right? What happens is gender means you could have values male and female, but when you are getting it into R, what generally happens is R by default assigns a codification to it. So it may say F means 1, M means 2, and it will get this codes associated with each of them into when it is bringing the data from a spreadsheet into R. So it will represent and it will store them as 1, 2 rather than male, female. And this kind of quantification or a codification that is being done to a categorical variable, that is what we call as factors. So factor is a feature that represents a characteristic which is having different categories of values. So just like this gender, it has different categories of values, male and female. So we call those kind of data as a nominal data. So factor is a kind of a quantification of those kind of categorical variable. So it is solely used for representing nominal variable. And if I am storing these categorical variables as male and female, there is a lot of memory that is required. But if I am storing them as 1 and 2, the memory saving is going to happen in the process. So there is a quantification that is being done, and there is a lot of memory saving. because labels are assigned to each of the variable, each of the categories of this categorical variable. So even if we get the data in the form of male, female, so let's say the data is like this. Let's say there are 5 people, male, female, male, male, female. Then if I say factor of this one, m comma f comma m comma m comma f, what typically it does is internally it assigns f equal to 1, m equal to 2, and it will store them as 2, 1, 2, 2, 1 kind of stuff rather than storing them as m, f, m, f. So it would be helpful for model building processes also at a later point. We would be talking about any model that we are building requires the data to be in a quantitative form so that the model can be built more effectively. So a good understanding of the factors is also very much required. Then the other structure that you need to be comfortable with is a list, especially for storing an ordered set of values. We would be seeing at a later point that many of the machine learning models that we are creating, the output of majority of these machine learning models will be stored in the form of a list itself, because list actually allows different types of values to be collected. So there could be a few integers, there could be a few numeric, there could be a few characters. So different types of values, whereas in case of vector, all of them should be of the same type. Whereas here I can get different types of values. So probably I can very well say list of vectors. Right? Vector is of one type. So probably I could have a vector A1 which is numeric, a vector A2 which is characters, vector A3 which is logical, and I can combine all these 3 vectors into a list, right? So various types of input and output data are typically stored in the form of list, and lots of usages come because majority of the machine learning models, they produce the output in the form of a list itself. The reason being, there is no restriction in terms of the number of elements, right? Each element of the list could be of a different size. A1 could be having 4 elements, A2 could be having 8 elements, A3 could be having 3 elements. Still I can create a list out of them. Whereas when we talk about a data frame, that can't happen. Though these could be of 3 different types, but all of them should have a same size. That is when I can create a data frame. But if they are not of the same size, then it's better that I create a list out of it. Right? So list as a function can very well help me in terms of creating a list out of the various vectors. And I can very well access. So here, if I'm saying A is a list of A1, A2, A3, so A will become a list. And if I say I want to access A1 out of it, I can very well use a dollar notation and give a naming $A1. So out of this list called A, pull out this element or the subset of it called A1. So you can directly access it by the name rather than by the position. So again, I want you to read through the list in depth by looking at a detailed introductory course on R, which will give you many more functions, how to do a subsetting of a list, how to extract the various elements from a list, all those typical aspects. Similarly, the data frame, the most important R data structure, especially when we are pulling the data from a spreadsheet or a database, we would generally try to store that in R in the form of a data frame. So data frame is also a list of vectors and factors. The only thing is number of elements should be the same for all the vectors. I can't have different vectors of different lengths. Different types is possible, but different lengths is not possible. When I have different lengths, then I should think of using it as a list rather than as a data frame. So data.frame as a function I am going to use. So data frame is always a two-dimensional. It has rows and columns. So it's always displayed in the form of a matrix. So I can always access the data frame A of 2, 3 means bring out the second row and the third column value for me. That is what is A of 2, 3. Or if I am saying A of 2, blank, it means pull the second row and all columns. Or if I say comma 3, pull all the rows, third column values. So this is how I can very well access the data frame. So position wise I can access this like this, or I can give a name. If I know the heading of the third column, so let's say third column heading is A3, I can access this through a name. So A is the name of the data frame, A3 is the name of the column, is the heading of that column. I can very well access the third column values quite comfortably using $A3. So again, I want you to spend more time in terms of understanding the data frames in depth by referring to any of the basic introductory courses on R. You can refer to my videos itself, introductory data analytics using R. Similarly, matrix, another structure more similar to a data frame itself. It's also a two-dimensional table, rows, columns, everything remaining the same. Whereas in a data frame, I can very well have any data type. So one column could be a logical vector, the other column could be a character, the other column could be numeric, whatever. Whereas in matrix, all the data should be only numeric. So it stores only numeric data. We use a lot of mathematical operations, right? We'll try to do a matrix multiplication, we'll try to do determinant of a matrix, we'll try to do inverse of a matrix for various applications. So for performing various mathematical calculations, we are using the matrices. So that's where it's a separate data type altogether. Again, just like a data frame, I can very well access the matrix as well. Even the extraction is more similar to a data frame. I'll give the square within the square bracket, I'll give the row number and the column number notation to extract the subset of that particular matrix. If I leave this part blank, it means that all the rows of this particular column will be extracted. If I leave this as blank, all the columns of this particular row will be extracted. So the subsetting of a matrix, subsetting of a data frame, you need to be comfortable with all these aspects, because we would be using all these aspects quite frequently once we get the data. And multi-dimensional, anything more than 2 dimensions if I have, I would treat it as an array. So it may be like a 3 by 4 by 2 array, which means it would be represented as 2 different matrices of 3 by 4 size. So that is what it is being called as an array. I have 2 3 by 4 matrices. So the third dimension will be repeated across the first and the second dimension. Basic understanding of all these aspects is very much essential before you go ahead in terms of cleaning the data, before you go ahead in terms of applying any kind of a machine learning algorithm to your data. Alright. Now, once I have a good understanding of the various data structures, then a few important aspects of managing data with R. So I should be comfortable in terms of saving and loading the R data structures. So whether we are talking about data frames or lists or any of them, I should be able to store them, save them, and I should be able to retrieve them. So save as a command will save the data frame. I can save the vectors, factors, whatever, so that I can use them at a later date. I can load them, again already created data which is stored as a part of our data file. I can give the name of it and I can load. So these are some of the things which I have already covered in depth as a part of my introduction to data analytics using R. So you will have a very good understanding if you refer to those videos, or probably you can very much refer to any other initial learning material with respect to R. Similarly, save.image is writing the whole session to a file called r.r data, which you can load for a later use. And if we are having the data in the form of an Excel file or a CSV file, you can do a read.csv, which will load the CSV file into the R. I have to specify the full path. If it is outside the working directory, that is what we are going to do at a later point when we are practically working with the data. By default, R assumes that CSV file has the header name. So if I have to write something to a CSV file, I can use write.csv. So these things will help us in terms of input and output operations from the external data sources into R. I can get the data from CSV files, or sometimes I can directly connect it to SQL database using ODBC connectivities. I can use SQL to really extract the data from various databases, for which we can rely on our ODBC package. Even this you can read it from other sources, or probably you can refer to my videos on data analytics using R, where this is also being covered in depth. Then we will take one example now, where we will be talking about exploring and understanding the data. So we have to understand that every data is unique. We have to understand the various aspects of the data, so that I can see which machine learning model will be more and more appropriate to this data, to what extent my data would be able to accommodate this particular model for the learning purpose. So once we load the data, let's load one data, right? That would be more comfortable for us. So let me load the data here, which is present in my Edge training videos, R datasets used car.csv. So I'm loading this particular data. So this is the way we load any CSV file. Because it's a CSV file, I'm using the function called read.csv. I'm giving the full path because it is outside my working directory. I'm storing this entire thing into a variable called cars, and this cars is a data frame. Oh, I did not give the name. Sorry, let me give cars. Right, I'm giving a data frame name called cars. So this is how. Let's check what is this cars all about. So I'm checking the class of this cars. It comes out that it is a data frame. So the CSV file, when you are importing it using the read.csv into R, it would be stored as a data frame. Now, first and foremost thing, explore the structure of the data, right? So the structure of the data frame, I will explore it using str. So I am saying str cars. So it's a data frame containing 150 observations. 6 variables are there. Year. So this is a used cars data. Year is an integer. 2011, 11, 11, 12, 12, some of the samples, first few observations. So it is treated as integer year. Whereas the model, it's a factor with 3 levels: SC, SCL, SCS. These are the 3 models of cars that are typically represented. and because these are character vectors, character variables, when I have taken the data into R, they have been converted into factors by default. Similarly, price. Price is an integer, so which is specifying the price of all those cars. Then I have mileage, which is also an integer specifying the mileage of each of those cars. Colors, I have it's a factor variable with 9 levels: black, blue, etc. So it's like black will be coded as 1, blue will be coded as 2, and so on. So there are 9 such kind of colors that are there. Transmissions is also a factor with 2 levels: auto and manual. Auto will be coded as 1, manual will be coded as 2. So this is what is the structure of the data frame. Okay, fair enough. Model is a factor, understood. Price is an integer. Mileage is an integer. Color is a factor. Transmission is a factor. But I don't want, let's say, year as integer. Right? I don't want, this is a year of manufacture of that particular car. So I don't want this year to be an integer, because I don't want to perform any kind of averages and all on the year. So I want, let's say, year as a factor. So what is the way I will convert it? I'll say cars dollar year, which is nothing but the data frame name dollar the column name. So I'm trying to overwrite the same. So that part I'm writing it as factor of, or probably I can use as factor, as dot factor. I'm converting the existing type to a factor type. What is the existing variable? Cars dollar year. So what this function does is, it will currently take cars dollar year, which is within the current cars data frame, the year column. It will take that, convert that into a factor, and assign that to this particular variable, which means it will overwrite the values of the existing variable. So this is how I am overwriting the year, which is an integer. I am trying to convert it into a factor. So by looking at the structure, I'll get an understanding, are these data types more or less okay for me, or should I need to convert any one of them to some other type, just like this example. So again, I can refer to the structure of the cars. It says yes, year is a factor now with 13 levels, 2000, 2001 and so on, so that I can do the comparison across the years, or I can do something. So that is where I wanted it as a factor, not as an integer. Alright, so that is the first thing I have done. str is giving the structure of a data frame or any other data structure also, right? I can use the structure on vectors, I can use the structure on lists. So it will give me the complete outline for the data dictionary. Then I would typically explore both the numerical variables as well as the categorical variables. I'll try to do a quick summary of all the variables. So I'll use a function called summary. These are very common steps which we have to do. Any kind of a data that is being supplied to us, any kind of a machine learning algorithm that we are supposed to fit to the data. So I'm doing a summary. Summary will give me some basic insights of each of the variables. You see year. Year, because it's a factor, it will do the counting of all the various possible values. So 2010, there are 49 occurrences. 2009, there are 42 occurrences. 2011, there are 16 occurrences. So the top 6 of them will be counted and presented, and all others will be going into a category called others. So there are 12 belonging to the other years, and these are the top 6 frequencies with respect to the year. Similarly, in case of models, SE model is 78 occurrences are there, SEL 23, and SES there are 49. So even that it would be represented with these kind of frequencies as well. So because these are all factor variables, The summarization will happen in terms of counts. Whereas price and mileage, they are integer variables. Because they are integer variables, you will find this kind of computation being performed for the minimum value. What is the minimum price in that list? 3,800. The maximum value, the mean value, which is the average, the median value, the first quartile and the third quartile. So these are the various things that are typically computed for quantitative variables and are being displayed, right? So these are the 6 things. Even in case of mileage, this is the minimum mileage, this is the maximum mileage of the cars that are listed for me, this is the mean value, this is the median value, this is the first quartile, this is the third quartile. So these are some of the things that I am looking at. Similarly, color wise, black has come 35 times, silver is present 32 times, red is present. So there are 35 black colored cars in that list of 150, 32 silver colored ones, 25 red colored ones, and so on. Transmissions wise, there are 128 cars with auto transmission and 22 cars with manual transmission. So that's how the listing is typically done. Now, so we are looking at the summary statistics. Now, few important points that we have to look at from the summary statistics out here, especially for numerical quantitative variables, price and mileage. I will be seeing how far is the mean and the median. Is there too much of a difference between the mean and the median? So if you see here, the median is 13,500, mean is 12,900. Yes, mean is smaller than the median, but the difference is not that significantly higher, right? Not too much of a difference between the mean and the median in terms of price. Whereas if you look at it in terms of mileage, median is only 36, whereas mean is 44,000. I could see that the difference is much higher in terms of percentage. So this is where I can say, in this case, mean is very high compared to the median. So there is a possibility of a skewed data. And that skewness is positive. When mean is very highly greater than the median, I can very well make a comment regarding a positively skewed data. When mean is very much less than the median, I can very much comment on negatively skewed kind of a data. Means there could be a few observations where the values are extremely higher. If it is a positive skew, I can talk about a few observations which are extremely higher compared to the other observations. Now that is what we are calling as a positively skewed kind of a data. Right? Some observations are extremely higher compared to others, and mean is very highly sensitive to the outliers. So we can very well see that the mean will be shifted very high or very low by the presence of those extreme values. So all the analysis will get very heavily biased because of this. So while looking at the data, we typically have to assess, especially when I am talking about the quantitative variables, we need to assess whether the data is more or less symmetric, or do you observe more and more positive or negative skewness present in the data. And to be much more appropriate, rather than loading the summary, I would prefer loading a package called Psych, right? So you can install the package called Psych, right? You can install it from this packages, install packages, and you can go to Psych. Or once it is already installed on your system, you have to load it using the library. So you say library Psych. It's already installed on my system. So once it is installed, I load it. So library Psych. This library has an important function called describe. So I can do describe cars. I can do a describe of cars. which will give me, you can ignore the factor variables, look at only the quantitative variables. So there are 150 observations, the mean value is 12,961. It also gives standard deviation 3,122. This is the median. This is the trimmed mean, means after it removes a few outliers, extreme values. This is the mean value. So after removing some of the outliers, I could see that the mean and the median are more or less coinciding out here. Right, this is the median, this is the trimmed mean. So they are more or less coming closer. Mean absolute deviation is this much, minimum value is this much, maximum value is this much, range, which is the difference between the maximum and the minimum, is this much. The skewness is being shown as minus 0.42 because the mean was lesser than the median. It is an indication of a negative skewness. But what we generally say is, as long as the skewness is in the range of plus or minus 0.5, again this is just a simple ballpark estimate. As long as the skewness is in the range of plus or minus 0.5, I can very well assume that it is around 0 itself. But the moment it crosses drastically this 0.5 limit, then I may have to really make a conclusion that the data is not symmetric. There is some level of either positive skewness or negative skewness that is present in the data. And same is the interpretation I make with kurtosis. Even the kurtosis value, which is an indication of fat tails present, extreme values are very heavy. More number of extreme values. That is what is indicated by the kurtosis. So if there are very few reasonable number of extreme values, the kurtosis will be around 0. Again, I can talk about plus or minus 0.5 to be the range, optimal ballpark kind of a range for 0. But if it is too highly deviating from 0, then also we talk about the presence of very high number of fat tails. Presence of fat tails or much heavy presence of extreme values and outliers in the data. So it is very much essential that I handle those kind of extreme values so that my analysis comes more and more appropriate. So that's one of the prime reasons for a quantitative variable. We would be looking at the skewness and the kurtosis values. So here, in case of price, I can safely assume that it is pretty much in the normal range, right? Because both of them are in the range of 0 to plus or minus 0.5 kind of a range. Whereas when it comes to mileage, I see skewness is 1.23, much above the 0.5 range. Even the kurtosis is 1.5. So both of them are looking much positive, which is an indicator that one, fat tails are present, two, the data is very much skewed to the right. So two of these things we are trying to assess just by looking at the initial summary statistics of the data. So that's the first thing, right? In some cases, if required, I may have to do the transformations, I may have to remove the outliers, some of these aspects, if I want to really derive some useful information out of the data, if I want to build a very sufficient, sophisticated model for my machine learning process. Then, the next part we talk about in understanding of the data, we are visualizing the numerical variables using the box plot. So I can very well say box plot, wherein I'll take cars, dollar, price. So the box plot is helping me in terms of identifying if there are any extreme values that are present in the data. So this is how the box plot is getting represented, right? I could see two, so this is the median value. I don't want to discuss too much in depth. This is the median, this is the third quartile, This is the first quartile. This is the maximum of the minimum value of the data, or the first quartile minus 1.5 times the interquartile range. So that would be this particular value. Whereas the upper whisker is more like it's the minimum of the maximum value, or Q3 plus 1.5 times the interquartile range. And any value that is above this upper whisker or below the lower whisker, they are typically treated as extreme values that are present in the data. I should be able to handle these extreme values because they can bias my conclusions much heavier. So when I am looking at the box plot, it is displaying the center. Center is displayed through the median, not through the mean here. And it's a spread. The spread is not in terms of standard deviation. Spread is displayed in the form of interquartile range, Q3 minus Q1. Spread is getting displayed through this mechanism. So it's also giving me the range. The range is from here to here. This is the range of the data. From here to here is the interquartile range of the data. And it's also giving me the skewness, because if these two are more or less symmetric, more or less equidistant from the median, I can say that the skewness is much lesser, overall symmetric. But if I say that this is very close and this is much farther, or this is very close and this is much farther from the median, then I can very well talk about the presence of negative skew or positive skew in the data. So it gives me all the three dimensions: the center, the range, which is the spread, and even the skewness. So a lot of things conveyed in one single diagram. So that's one of the prime reasons we use the box plots. Now the width of the box plot is arbitrary. So there is nothing, even if it is too fat or too thin, there is not much of an information that I am deriving through the width of the box plot. It's only through the length, all these outliers, extreme values denoted with circles. So that's how it gives me an overall picture of whether my data is more or less normal, or I find too many abnormal values present as a part of the data. So this is how we are getting it for price. But let's say I want to look at it for mileage, not price. Price, we anyhow got it, it is very much closer to normal. So you don't find too many extremities in the data. But look at the mileage. So median, Q1, Q3, minimum. Now you could see the distance between this median and this lower whisker is much lesser, whereas median and the higher whisker is much higher. Now this is what will indicate that there is a presence of positive skew in the data. And you could also see that so many outliers are there on one side, and probably this one is much away from the rest, or probably even these two are slightly away from this line. So a few of them are just away from this upper whisker, so just outside the acceptable range, but a few of these are much far away, and those are the ones that are carrying the mean much away from the median. So we need to have some kind of mechanism to handle those kind of numbers, so that we can bring a much better picture regarding the modeling of the data. So that's one more important aspect that we need to look at. So the box plot helps us in doing this kind of summarization, helping us in terms of identifying how the data is more or less spread. So it is giving me the center of the data, it is giving me the spread that is present in the data, it is also giving me the presence of skewness, and along with that the different kinds of outliers that are present in the data. All those are being brought out by looking at the box plot. Another way we generally visualize the numerical variables is through a histogram. So let me do a hist. Again, cars dollar price. I'm doing a histogram of cars dollar price. So this is how the histogram is broken up. You could see here the intervals that are being created. Overall, you could see the pattern, like there is some kind of peaking in the middle. More number of observations are there, somewhere between 12,000 to 15,000 or 18,000 kind of a range. Very few observations are there below 5,000 and about 20,000 kind of values. So that is what is being given by the histogram, right? I could clearly see that the histogram is dividing the variables values into a predefined number of portions called bins. So if I say I want to create a better brakes, you give your brakes, otherwise it's a default thing. So you can give it as a sequence of, so what do you want to put? 0 is the minimal, to the maximum value is, let's say, 25,000, and you put a break of 1,000 per each, right? So that's the breaks you want to define. So this is how your histogram is going to come out. 0 to 25,000 is the limit, and 1,000 is the size of each class. So you could clearly see that this is the class which is coming out. And so so these are the three ranges where maximum number of cars are priced. Overall, it is looking like some kind of a symmetry that is present. So still, though it is looking more skewed towards the left, overall I could see a decent amount of symmetry when I am doing the histogram of the price. Whereas when I am trying the same, instead of price, let me try it on the mileage. Okay, so the mileage numbers have to match first of all. So first let me not use the brakes directly. Let me see what is the range of the mileage. So it's almost going from 0 to 150,000 and more. Let me see what are the values for the mileage. The minimum is 4,800 and the maximum is 151,000. So my brakes need to cover that area. So I will give the brakes saying sequence 0 to 160,000 with 5,000 as the brakes. Okay, so this is how the histogram of the mileage is coming out. You could see that the peak is there somewhere below the 50,000 range, but you have the observations much closer towards much above than the 150,000 range as well. And you could see this range does not have even a single vehicle. So which is what indicates that these all could be different outliers that could be present in the data. Very extreme values. You will hardly find one or two observations that are falling in this whole range. So these would be categorized as very extreme values, and we need to have a mechanism to handle those extreme values. So it can use any number of bins. Either we can specify them using the brakes, but all the bins will have identical width. But if you see, the frequencies are based on how many values are typically present in each of these bins. So that's one more thing. Any data that is being given to us, I quickly explore the visual aspects of that data, which talk about the presence of outliers, the presence of symmetry, skewness, spread, center, etc. by looking at the box plots as well as the histograms of the data. Then, what kind of distribution that particular is the data more or less normally distributed? Very, very essential aspect, because we will be seeing later that many statistical models that we are going to build, they assume the data to follow a kind of a distribution, a particular distribution, which are called as parametric models. So if I am trying to build a regression model, it assumes that lot of data follows a normal distribution. If I am executing correlation on the data, it assumes that my data is following a normal distribution. So when I have to use those mechanisms or those models on my data, I have to be very much clear that the data is more or less normally distributed, which is other way of saying that the skewness should be very close to zero, and kurtosis value also should be very close to zero to ensure that the data is more normally distributed. Now, to understand whether the data is normally distributed or not, there are various mechanisms. One, we can use a quick formula called Shapiro.test. Shapiro.test will assess whether this particular column is normally distributed or not. Shapiro.test, I give the input cars dollar price. Right? Instead of giving a detailed explanation of this test, I'll give you a quick interpretation. So here, the test makes a few things. So regarding this test, you always remember the null hypothesis for this test is the data is coming from a normally distributed population. Whereas the alternate hypothesis for this is the data is not normally distributed. Straightforward. So, and the way you interpret is you look at this p-value that your test is giving. So the p-value that I am getting is 0.0008. So you just check whether it is less than 0.05 or greater than 0.05. In this case, this number is less than 0.05. So if it is less than 0.05, you take your decision as alternate hypothesis. So this is always fixed. So you take your decision as alternate hypothesis. If it is greater than 0.05, you take your decision as null hypothesis. So because this is less than 0.05, we are taking the decision as alternate hypothesis, saying the data is not coming from a normally distributed population. So I can very well say price is not normally distributed. The same logic I'll execute it for mileage as well to check if the mileage is normally distributed. So even in this case, the p-value is 1.151 into 10 to the power of minus 8, which is also less than 0.05. So I'll take my decision as alternate hypothesis, which says the data is not normal. So if I go strictly with the normality test, I can very well say both the price as well as the mileage, neither of them is normally distributed. Right? So we need to have different mechanisms in terms of understanding how do I really try to make it more and more normal. So a variable distribute, or is it following any other kind of distribution? So there are so many such kind of distributions which are nothing but the frequency patterns, right? Probably if I am drawing a frequency histogram, I am getting some kind of a shape of the histogram. So that shape of the histogram typically they are mapped with some kind of theoretical distributions, and that is what is being assigned to this particular data, so that the further assessment of the data can become more and more easier if I am mapping the data to a particular distribution. So that is one way of checking for normality, and there is a graphical way of it as well, wherein I use a function called QQ norm. QQ norm, if I am using it on the price column, so it gives me a plot like this. If this plot is more or less a straight line, If this plot is more or less a straight line, then I can say that the data is very normal. But if it is deviating from a straight line, then I say that the data is also deviating from normal. So here you see so many curves that are coming up, not too much straight. So that's where it is deviating from the normality. The same logic, if I apply it for the mileage, I could see it's much more deviating from the normal because there's a lot of curviness that is coming as a part of the QQ plot. So this is one more way of understanding whether the data is close to normal or not. Right? There are so many things which people do. If the data is not close to normal, they try to do some kind of transformations on the data to see if the normality situation can be improved. They do a lot of transformations on the data, or in some cases they remove the outliers from the data to try to bring in more and more normality into it. So various kinds of mechanisms are being tried out on the data so that it comes more closer to normal, so that the appropriate machine learning algorithms can be very well applied to that particular data. Then once we are looking at the data, we are also looking at measuring the spread, the variance and the standard deviation of the data. So when I look at the variance, if it is very large, or standard deviation, if it is very large in respect to the mean, probably we have already done that here. For price, the standard deviation is 3122 out of a mean of 12,000, so approximately around 25%. Whereas in case of mileage, the standard deviation is 26,000 for a mean of 44,000, more than 50 to 60%. So you see that the standard deviation is much higher for mileage compared to that of for the price. So the larger is the standard deviation. Always remember the standard deviation, it's better to assess in terms of the mean. So if you look at for price, the standard deviation, if I am considering which is 3122 in terms of units, but if I am converting it in terms of proportion of the mean, it's around 24%, whereas in case of mileage, it's much more than 50%. So this is otherwise called as coefficient of variance, but what we are seeing is this is almost 60% here, this is only 24% here. So the larger the number, the larger is the spread in the data. There is a lot of variation around the mean, because as a simple definition, if I want to understand standard deviation, it is more like on an average how much each of these observations are deviating from the mean. So on an average, each observation is deviating by almost 60% from the mean, whereas here on an average the data is deviating by around 24% around the mean. And used to quickly estimate how extreme a given value is. If it is a normally distributed data, how much extreme the value is, because what we typically say is, if it is normally distributed data, there is an empirical rule which says approximately 68% of the data will lie between plus or minus 1 standard deviations of the mean. Similarly, 95% of the observations will lie between plus or minus 2 standard deviations of the mean, and 99.7% of the observations will lie between plus or minus 3 standard deviations from the mean. So in this case it says, right, if I go with this is the mean plus 3 standard deviations from the mean. This is the 3 standard deviations from the mean, 22,000, and if I am taking the minus, so it says 99.7%. if this is normally distributed, if the price is normally distributed, 99.7% of the observations will lie between 3,594 and 22,329. Only 0.3% of the observations will be either below 3,594 or above 22,329. That's a quick way of understanding to what extent my data can go on either of the extreme if the data is not normally distributed or if the data is normally distributed. So values more than the 3 standard deviations away from the mean generally are rare events. They occur very rarely, and that is where we should not we should handle them separately. We should not consider them as a part of the regular model building process as such. Then if I am having categorical, so these are all the things that I have to look at if I am having numerical variable. But let's say I am having categorical variables. So there is nothing much I can do for categorical variables. There is nothing called mean, median, standard deviation, skewness, etc. for categorical variables. Here, when I am using the word categorical, the structure of it being a factor. So all I can do on those things is the tables itself. So if you look at, let's say the color table, I'll create a table saying cars dollar color. So it says there are 35 black cars, 17 blue cars, only one gold car is there, 16 grey cars, 5 green, and so on. So it's a kind of a tabulation that is occurring. And if I want it in percentages rather than in terms of counts, I can simply put prop.table, which is proportions table, and this would be on the table that is computed. Already the table that is created, I put a prop.table on the top of it, which will give me, or if possible, probably will do the rounding also, so that it doesn't give me such kind of odd. So I'll put it as rounding, let's say to 3 digits after the decimal. So the black is almost 23.3%, blue is 11.3%, gold is only 0.7%, gray is 10.7%, and so on. So I can very well create a table, understand how many colors of each kind are there, right? How many cars are there of each kind of color, and similarly I can also look at the proportions associated with them. So let's try out something more. Let's say instead of color, I want to look at the model. So it says almost 52% of the observations are SE model, around 15.3% of the observations are SELs, and almost 32.7% fall under SES model. So it can give me a quick understanding. Similarly, if I am looking at the year is also a factor variable. So it says 20% of the 2% of the observations are belonging to 2000, 0.7% in 2001, 0.7% in 2002, probably 28% of the observations are from 2009, 32% of the observations are from 2010. So it gives me a quick assessment of which kind of cars are getting sold more. Probably I say the cars that are manufactured in 2009 and 2010, they are getting sold more heavily compared to the other set of cars. Then the other thing that I can look at, the central tendency, which is the mode, which we have already evaluated now, the one that is coming with the maximum frequency. So 2010 comes out as the maximum frequency here, and similarly I could see SC is coming out with the maximum frequency here. So the mode is more like the element that is coming with the maximum frequency. So I will see which particular variable is coming with the maximum frequency. Graphically also I can use a bar chart, or probably I can simply use a plot Plot is, if I am giving a categorical variable as an input, the plot will typically plot a bar chart only. So I could see that for 2010 there is a maximum frequency, and even for 2009 the frequency is much higher. But for all the earlier years the frequencies are much lesser. So the bar chart is giving me the basic quick understanding in terms of the model value, right? Many a times there could be a uni model, but of course if the number of categories are very few, there is a possibility of bimodal or even multi-model. If the data set is very small, there is a possibility of bimodal or multi-model as well. So we generally don't have a mode for a quantitative variable because almost any value is possible. So I don't expect a particular value to be repeated more number of times, because the precision could be of any kind of decimals, any kind of digits after the decimal point. So generally we don't define the mode for a quantitative variable. But when we are talking of categorical variable, the one that is coming out with the maximum frequency is what is being considered as a mode. So that's one more thing that we typically look at. Then we also consider the relationship between the variables. So the relationship between the variables, so there could be bivariate relationships. We are taking two variables together, right? If we are talking about the quantitative variables or the categorical variables, the things are going to differ in terms of the relationships. So one, I look at the pairs of variables. So one of the important tools that I can use for two quantitative variables is I'll try to find out the correlation between the variables. So I'll say cars dollar price comma cars dollar mileage. I want to see the correlation between these two variables. So it is coming out to minus 0.806, which is a negative value. Generally correlation will lie between minus 1 to plus 1. So very much closer to minus 1 indicates a strong negative relationship between the variables. So if one is higher, the other one is going to be much lesser, and vice versa. So one basic thing I can conclude here is, as the mileage is much higher, I see that the price of the car is going down drastically. So the car which is used more, which has been driven for more number of miles, obviously the price of that car is much lesser. But still the number is not minus 1, which means it's not a perfect scientific relation. For every 1 mile increase, the price will decrease by some specific amount. It's not a 1-to-1. It's only in majority of the cases it is showing that kind of an opposite relation, whereas there might be a few cars which are having a higher mileage, but still the price of them is much higher compared to a few other cars which have a lower mileage as well. So that's one thing that is coming out in this relationship. Sometimes I may be interested in doing a multi-variable relationships also. All the variables, between all the variables, I would be interested in looking at the relationships. Now this is where I can use the scatter plot if I want to visualize all these relationships. So if I am giving multiple variables, the whole data frame as an input to this plot function, it will perform the scatter plot for each pair. So there are 6 variables altogether. So this is a plot between year and model. This is a plot between year and price. Now let me tell you, out of this whole scatter plot, there is no point in interpreting each and every aspect. The scatter plot wise, what makes a lot of sense for me is the plot between only the quantitative variables or continuous variables. So here we have only 2 continuous variables. One is the price, the other one is the mileage. So only this plot is very much important to me. This is between price and mileage, or probably if you look at column wise, price and mileage. So only these two plots are very much important to me. All other plots are of no use because they are all different qualitative variables, categorical variables. So I don't rely on the scatter plot for the categorical variables, because the way it plots them is based on converting them into a codes 1, 2, 3 assignment. So there's no point in trying to interpret those values. So it's as good as I would have done, instead of plotting the whole columns, I could have done cars dollar price, comma cars dollar mileage. Just take between these two. One single plot would have done the job for me. So I could see a kind of a falling relation. As the price is increasing, the mileage is decreasing. Or if I can plot it the other way also. So first let me, on the x-axis, let me take the mileage, and on the y-axis let me take the price. What I could see is, as the mileage is increasing, the price is decreasing, and vice versa. So that is what we call as a scatter plot. So between every pair of variables, it will show me a relation, but generally advise that you use it only for quantitative variables. So one feature is taken on the x-axis, the other one is taken on the y-axis. It will show me, as the values of x is increasing, what is happening to the values of y. Is there some kind of a relationship that is existing between x and y, or they are more or less independent? And similarly, we have used the numerical value called correlation, which is giving me the strength of the association. So if it is very close to -1, we say it's very strongly negatively related, these two variables. If the correlation is close to +1, I say two variables are very strongly positively related. If the value is very close to 0, we say that they are not linearly related at all. So if the correlation is positive between the variables, we see that the scatter plot will keep sloping upwards. So the points will be more like this, whereas in this case they are more like this, sloping downward. So it's an indication that the relationship between the variables is more and more negative, not positive. Then, when we are talking about two categorical variables, we are trying to understand the relationships using the two-way cross tabulation. So for that, again we can use the table. So we will take cars dollar, let's say model as one of them, and let me take cars dollar color. So for each model, for each color, let me see how many are coming out. So these are the total black. SC model, there are 19 of them. SCL model, there are 3 of them. SES model, there are 13 of them, and so on. So the blue, it is like this. Gold, there is only an SC model, but I don't have SEL and SES model in terms of gold cars at all. Similarly, green, I have only SC and SEL models. I don't have SES model at all. Yellow, I have one of each of these three kinds. So you could see very clearly the distribution between these two categorical variables. So I can create a kind of relationship between the two categorical variables using the table, right? Or much more detailed, if I want to get, better load the G models package. Right, I think I should already be there on my system. So I will load the G models package. No, it's not there. So let me install this package. I'll install it from India, but you can choose any of your locations. Okay, so let me install the G models package. So any package that you are using, once you install it, you have to load it using the library. So first let it install, then I'll load it using the library function. So now this package got installed. I will load this package. Alright. So the package is loaded. Now I have to use a function called cross table. Yes. So if I don't know how to use this function, it's always better to type in with a question mark. So you will get a clear help on how do you need to give the inputs to this particular formula. So cross table actually requires x comma y. So x is a vector or a matrix. This is where I have to understand the data structures. X is either a vector or a matrix. So if y is specified, then obviously x has to be a vector. Similarly y. So I have to give both x and y. If you see the cross table, it's an implementation of a cross tabulation function with output similar to cross tabs procedure that is there in SPSS or SAS. So it will give me the chi-squared value, the Fisher-McNamara tests of independence. Fair enough. So we may not be using them, all of them right now. We will only look at the proportion, the basic table, right? So if I just give x and y, these are the only two mandatory variables that I have to give. So let me do a cross table, right? X I will take as cars dollar model and y I'll take it as cars dollar color. I'll get a much better representation here. So what you could see here, let me close this graph. What you could see here, these are the various things that this cross tabulation is giving. Okay, a C model, 19 of them are total, but it is giving me in terms of percentages as well, right? So it is saying 0.035 altogether, and this is as a part of the overall proportion, whereas here it is also giving me in terms of the row breakup. The overall row total is 78, which is 0.52, 52%. But out of this 52%, I could see that here it is 24.4%, 11.5%, and so on. Similarly, when I look at the column total out here, it is overall 23.3%. So within this 23.3, again it is doing a breakup across the groups. So it is giving me in a kind of a tabular form the frequency, as well as it is also giving me in terms of proportions of row totals as well as column total. If you see here, this is what it is talking of. First it is in terms of n, then in terms of the chi-square contribution, then n divided by the row total. So this is n divided by the row total, which is 19 by 78. 9 by 78. So this is n divided by the row total. The next row gives me n divided by the column total, 19 by 35. 3 by 35. So these are n divided by column totals. And the last is giving me n divided by the table total. So this is like 19 divided by 150, which is 12.7%, and so on. So I can very well use all these variables, right? It is giving me a much more detailed picture compared to my simple table function. So in many cases, I would like to use this cross table compared to the usage of the regular table values itself. But it will help me in terms of exploring the data more and more in terms of the depth. Then, So if the groups are required to be merged, we can very well merge them as well. Here let me not look at that particular aspect, wherein I can very well set percentage in percentage operator, right? So I can very well set the groups. I can think of clubbing some of the colors, right? Let me look at some of the colors, probably gold, green, yellow. I'll try to club them, right? So I'll say cards dollar color. I'll try to overwrite on that same cars dollar color, wherein if else, I'll try to put if else, right? I'll first let me try to card. Okay, let me create cars dollar color, which is giving me, if it is green or gold or yellow, it should be treated as true, otherwise it should be treated as false. So that is what I'll call it, cars dollar color. I'll say cars dollar color percentage in percentage. So if it is present as a part of, I'll give a C concatenate operator, wherein I will specify gold, green, and let's say yellow. So what is that I am trying to do here? I am simply saying the cars dollar color, if it is one of these three colors, then it will be treated as true, all others will be treated as false. So that's one thing. So if you are looking at now what is coming out as a part of cars dollar color, you will see that, okay, the first one is coming out to be true, this one is coming out to be true, and many of them are coming out to be false. If you try to do a table of this, you will come to see that only 9 of them are true, remaining all of them are false. So there are 141 falses, 9 trues, because wherever it came out to be gold, green and yellow out of the data, it is assigning as true, otherwise it is assigning as false. So now what I can very well say is, I will rewrite the same cars dollar color. So it has now become actually false and true. I should have taken it as another variable. Fair enough, but now it has come out as, because I have overwritten the same, now they have become actually false and true. So now I can very well take out the special colors separately and the regular colors separately, and try to see which of them are being distributed across each of the model. So if you had taken them as a part of a new variable, it would have been better. Instead of cars dollar color, if I had taken it as a color 1 or something, it would have been much better, because now it have actually become false and true. The original values of the color are typically lost. So if I have to continue, I have to continue right from the beginning. But yes, I am giving you in here, take it as cars dollar color 1, then your original values also will be retained, and even the true and falses also will be retained. So you can even merge the groups in this way, especially if there are one or very few observations in each of the groups, so that you can understand the things much more better. Right, by using the percentage in percentage, you can even merge the groups to understand the groups much better. Sometimes you can also use a Pearson's chi-square test for the independence. So there also, when you are taking, okay, let me take the variables, that would be much better. Then let me recreate the data. So I am using this data again. So now that everything is there as a part of the cards, so I will use all else is fine. So let me simply take the groups, because I am using the G model, so I'll take the cross table, where I'll take cars dollar model, comma cars dollar what is that color, and if I want the chi-square test, I'll simply put chi-squared equal to true. Now what is that we are trying to understand is the null hypothesis in this test says that the proportions are more or less uniform, proportions of one variable are more or less uniform across the other variable. Otherwise people say here the proportion of the colors is more or less uniform across the three models. So it's not like some models have some specific colors, some models are biased with some other color. The proportion is more or less uniform across the model. That is what is being specified by. So there is no relationship, or models and color are independent. That's one more null hypothesis people said. There is no relationship between the models and the colors. The proportions are more or less uniform. So if I am looking at the proportions of green out of the total, this proportion is more or less uniform across SC, SEL, SES models. It's not that probably in case of SEL model the greens are much higher, whereas in case of SC models the blacks are much higher. It's not something like that. So that is what is the null hypothesis, whereas the alternate hypothesis says no, that is not the case. There is a significant difference in the proportions, which means for different models, different colors are dominating. So it's not uniform across the process. Again, I'm looking at the p-value. So the p-value is giving out to be 0.117. This is greater than 0.05. If it is greater than 0.05, always take your null hypothesis. So there is no solid evidence for me to typically say that the proportions are uniform, to reject that the proportions are different. So there is more or less, I am concluding that the proportions are more or less uniform across the models. And because the data is very small, even the reliability of the test also may not be that reliable. But yes, if I have large volumes of data, or in some cases this is where I may want to club, right? So what I can do is I will do cars dollar color, right? What I will set is I'll set cars dollar color 1, let me set, just to be on the safer side. I'll use an if else function, right? Cars dollar color, if it is in, so if it is in means I'll use percentage in percentage, right? If it is in, I'm taking it as green comma gold comma yellow. I'm just trying to club the groups. So if it is one of these three, then I will mention those as others. Otherwise, I will retain the cars dollar color itself. I'll retain their original color itself. So what we are saying is, if this color is any one of these three, I would call it as others. Otherwise, I would retain the cars dollar color itself. So let me see how it works out. Now let me try using the cross table again between these two. Again using the chi-square. Now we will not have 9 groups, 9 different colors. You should get only 6 groups. Right? If you see now, okay, I have to put it for color 1, because now we have made it as color 1. Okay, now if you look at the color 1, so you could see it is 1, 2, 4, 6, 7, 8. The values are just missing, and you are having others. The other 3 are clubbed together to form others. So that's where you have 9 cars of that particular group. And even here, the chi-square test is showing a p-value of 0.056, still greater than 0.05. So we will still go with the null hypothesis itself. But yes, this basic data setting needs to be more and more comfortable. Even if you see this particular group, the SCL and SES, they are just one observation. If the data is very small in any of the groups, the test will not be that much reliable. It is very much expected that we club all of them to produce a much better interpretation of the data. So in all this process, what is very much important for us to understand is when we are provided with the data, there is a lot that we have to work on it, get a basic hold of the data, streamline the data more and more appropriately so that a better test can be applied on the data. So that is what was the more important aspect in this particular session. I hope you got a basic understanding. You would be able to do all these preliminary aspects when you are supplied with any kind of a data. If you are having any other further queries regarding the same, feel free to get in touch with me on the number that I have provided below, or you can send in an email at the email address that I have given out there. Thanks a lot for listening to this session. Thank you very much.